Welcome to the deep dive. Today, we're kind of taking the hood off your GNU Linux system.
Yeah, looking right into the engine room, so to speak.
Exactly. Every single program you run, every process, it needs memory. And, for most people, memory probably feels like this one big swimming pool.
Right, just a giant space. But it's really not like that under the covers.
No, the technical analysis we're looking at today shows it's actually very structured, meticulously managed even.
Especially by two really critical regions that work together and sometimes seem to compete.
And those are the stack and the heap.
That's right. When your program is actually running at runtime, its data lives in one of these two places. And our mission today really is to demystify them.
Because understanding this isn't just like academic theory, is it?
Not at all. It's fundamental.
Yeah.
If you want to write software that's stable, fast, and maybe most importantly, secure, you have to grasp this.
Okay, so let's start high level. What's the big picture difference? Think of it this way. The stack is all about order and speed. It's automatic, very rigid, but lightning fast. Its contents, though, they don't last long, fleeting. And the heap?
The heap is the opposite in some ways. It's built for flexibility. Massive amounts of space, data can live for a long time.
But there's a catch.
There's always a catch. You have to manage it yourself manually. And, well, that manual part, that's where a lot of bugs, a lot of headaches come from.
Okay, manual versus automatic. To really get why they're so different, we probably need to look at the history, right?
Yep.
What problems were they trying to solve?
Exactly. They weren't just invented on a whim. They were engineered solutions to very real problems in early computing.
Let's start with the stack then. You said order. The core idea is LIFO, right? Last in, first out.
Yeah, the classic analogy is that stack of plates in a cafeteria. You put one on top, you take that same one off first.
Simple enough, but how did that solve a computing problem?
It was genius, really. It solved the problem of nested function calls. Imagine function A calls function B and B calls C. How does the computer remember, once C finishes, where exactly to jump back to in B and then back to A?
Ah, the return address. Without a system, it would just get lost.
Completely lost. The stack enforces perfect discipline for this. This whole idea was really formalized in the AlGOL 60 language, which kind of paved the way for modern programming.
So how does it work mechanically when a function is called?
A dedicated block of memory called a stack frame gets pushed onto the top of the stack.
Okay, and what's in that frame? Everything that function needs just for itself. Its local variables, any parameters it received, and that critical return address. And when the function's done,
Pop. The entire frame is instantly removed, popped off the stack. Execution jumps right back to the return address. It's incredibly fast, automatic. It's what makes things like recursion even possible.
wow, okay, that sounds almost perfect. Fast, ordered, automatic. Why would anyone not use the stack for everything? What forced the creation of the heap? Well, that perfect system has two big drawbacks: rigidity and lifespan. Rigidity, meaning
Meaning the size of everything on the stack, all those local variables, has to be known before the program runs, at compile time.
so if you need memory for something, like reading a file, but you don't know how big the file is until the user chooses it.
Exactly. The stack can't handle that dynamically sized data easily. Its size is fixed.
And the second problem, lifespan.
The data is ephemeral. As soon as that function frame is popped, poof, the data is gone, irretrievably. It only exists within that function scope.
Okay, so if you needed data to stick around after the function finished, or if its size was unpredictable,
You need something else, and that something else was the heap. Think of it as a big, general-purpose pool of memory, sometimes called the free store.
this is where you put data that needs to last, or data whose size you only know at runtime. And the name heap itself is interesting. The source we looked at points out it's just an analogy, right? Like a jumbled pile.
Yeah, it's important not to confuse it with the heap data structure you learn about in algorithms classes.
Yeah.
Totally different concept. This is just the big, messy area of available memory.
Okay, so who figured out how to manage this messy pile?
Well, languages like LISP were pioneers here. They needed dynamic memory and even invented the concept of a garbage collector, basically, an automatic cleaner-upper for the heap.
But that's not usually how it works in GNU Linux with C, right? We don't typically have that automatic cleanup.
No, generally not in C. We rely on manual control. The programmer explicitly asks for memory using a function called malloc memory allocation.
And crucial.
Crucially, they must remember to give it back when they're done, using free. That's the discipline required.
Okay, so the stack is automation station, super fast. The heap requires the programmer to take the wheel. Let's talk about the speed difference.
It's dark. Stack allocation deallocation. almost free. It's typically a single machine instruction. Just move the stack pointer, which is a special CPU register, up or down a bit.
Negligible cost. But calling malloc for the heap, that's different.
Oh, way different. Much, much slower. Remember, the heap is that jumbled pile. When you ask for, say, 100 bytes with malloc, the system can't just adjust a pointer.
It has to, sure.
It has to run a potentially complex algorithm. It searches through its list of free blocks to find one that's at least 100 bytes. Maybe it finds one that's 120 bytes, uses 100, and puts the remaining 20 back on the free list. It's work.
And freeing memory with free isn't simple either.
Nope. When you call free, the system marks that block as available again. But it also tries to be clever and see if the newly freed block is next to another free block.
Oh, to merge them.
Exactly. To try and combat fragmentation by creating larger contiguous free chunks. So, yeah, both malloc and free involve significant overhead compared to the stack's pointer flick.
Which brings us to size limits. The stack is fast but small, right?
Typically, yeah. It has a fixed size, often just a few megabytes, set when your program starts. If you use it all up, bad things happen.
We'll get to the bad things, but the heap.
The heap is generally large and flexible. Its main limit is just the total available RAM in your system. But that flexibility comes with that downside you mentioned, fragmentation, right? Because programs are constantly asking for different sized chunks, using them for varying lengths of time, and then freeing them in, let's say, a somewhat random order.
The free space gets chopped up.
Into lots and lots of small, non-contiguous pieces. It's like that parking lot analogy.
Right, you might have 50 empty spots, but they're all single spots, so you can't park your big truck that needs 3 spots together.
That's fragmentation. You could have gigabytes of total free heap memory, but if it's all in tiny fragments, you might fail to allocate even a moderately large buffer. It's a real performance killer sometimes.
So different designs, different jobs, different performance, and totally different ways they fail. One fails loud, the other quietly, you could say that. The stack failure is usually loud and clear. The stack overflow, you just ran out of that small fixed space.
Yep. Usually happens because of runaway recursion functions calling themselves too deeply, or maybe accidentally trying to put a massive piece of data, like a huge array, on the stack when it really belonged on the heap.
And the result?
Immediate. Program crash. Game over. The system stops it dead.
Okay. Dramatic. But heap errors, they're the insidious ones, the silent killers.
Often, yes. The absolute classic heap error is the memory leak.
That's when you call malloc but forget to call free.
Exactly. That piece of memory remains marked as in use by your program, even if your program has lost all track of it and can never use it again.
And the program doesn't crash immediately?
No, that's the danger. It just keeps running, leaking more and more memory over time. Slowly, steadily, it consumes system resources until maybe hours or days later, the application becomes unresponsive, or the whole server grinds to a halt. Very common problem in long-running services.
And leaks aren't the only danger with manual heap management, are they?
Oh, definitely not. The source material highlights other really nasty ones, like using memory after you've already freed it. That's called a use after free.
Uh-oh. What happens then?
Chaos, potentially.
Yeah.
That memory might have been given to some other part of the program, so you end up corrupting data you didn't intend to touch.
And the other big one mentioned is trying to free the same memory twice. Double free.
Yeah, that's also really bad. It can corrupt the internal bookkeeping structures that the memory manager itself uses to keep track of free blocks.
So that could lead to crashes later on, maybe during a completely unrelated malloc or free call?
Exactly. These heap corruption bugs, use after free, double free, are notoriously difficult to debug because the crash often happens far away in time and code location from the actual mistake. Nightmare scenarios for developers.
Okay, this sounds like they're almost enemies, the stack and the heap. But the real insight, the sort of aha moment from pulling this together is that they're not really competing. They have to work together.
Absolutely. They form an essential partnership. They're symbiotic. You always want to prefer the stack. Its speed and automation are just too good.
But you can't always use it.
Right. When data needs to live longer than a single function call, or when its size isn't known until runtime, then you reach for the heap's flexibility and large capacity.
So the fast engine stack needs a way to talk to the giant storage unit, heap. What's the bridge? How do they coordinate?
The bridge is the pointer.
Ah, the memory address.
Exactly. When your code calls malloc to get, say, a big chunk of memory on the heap, malloc doesn't return the data itself. It can't. The data might be huge.
It returns the directions.
Perfect analogy. It returns the address where that chunk of memory starts. This address is stored in a variable type called a pointer.
And where does that pointer variable itself live?
Ah, that's the crucial link.
Yeah.
The pointer variable itself, the address, the directions, is usually just a small, fixed-size piece of data. So it typically lives on the stack, just like any other local variable.
Whoa. Okay. So the fast ordered stack holds the small, efficient directions to the large, flexible, potentially messy data block residing out in the heap.
You got it. That's the core mechanism.
Let's walk through an example to make sure we've got it. Say I have a function create buffer.
Okay, create buffer starts running. It gets its own stack frame.
Inside create buffer, I call malloc to get, 10 megabytes of space on the heap for a data buffer.
Right. malloc finds that space on the heap and returns the starting address. Create buffer stores that address in a local pointer variable, let's call it buffer PTR, which lives in its stat frame.
Now, create buffer finishes its job. But before it finishes, it returns the value of buffer peer that address back to whoever called it, maybe the main function.
Okay, so main now receives that address and stores it in its own pointer variable.
Then create buffer ends. What happens to its stack frame?
Pop, it's gone. Instantly destroyed. The local buffer peer inside create buffer disappears.
But the 10 megabytes on the heap?
It's still there. It persists.
Yeah.
Why? Because main now holds the directions the pointer to it. The data's lifetime is no longer tied to create buffer.
It's now tied to main's logic. And main is now responsible for eventually calling free on that address when the buffer is no longer needed.
Precisely. That entire workflow is the heart of dynamic memory management in C and G and Linux. The stack manages the pointers, the heap manages the potentially large, long-lived data they point to. That really clarifies it. Stack speed, order, automation, short lifespan, heap, flexibility, size, persistence, but requires manual, careful management. And that's the key takeaway for anyone developing or managing systems on G and Linux. Our source material really hammers this home. Nearly all the really severe, hard-to-find bugs in performance instability, especially in C-based code, stem from getting this boundary wrong.
Mismanaging the heap, basically.
Yeah. Using malloc without the discipline of free. Using pointers after they're free, double freeing, leaking memory. You have to treat the heap with respect and discipline. Stick to the stack unless you absolutely need the heap's features. It really does boil down to those management styles, automatic versus manual. The stack is like that checklist you run through quickly and it resets automatically. Fast, rigid, but safe if used correctly.
Yeah.
And the heap is more like managing resources for a big long-term project. You have to deliberately allocate things, track them carefully, and make sure you clean up properly afterwards. It's slower, requires effort, and if you mess up the cleanup.
The consequences can be delayed but severe. Okay, that leads perfectly into a final thought for you, our listeners, to chew on. We've seen these two contrasting management systems in memory, automatic fast rigid versus manual slow flexible. Think about your own work or life. What systems or processes do you encounter that follow a strict, automatic, almost LIFO-like principle for speed and efficiency? Maybe like processing an inbox or following a strict protocol.
And contrast those with processes that require slow, deliberate manual allocation and careful cleanup afterwards, maybe managing project budgets, allocating team time, or even just organizing a complex event. Which of those two styles, in your experience, the automatic or the manual, tends to introduce the most dangerous, hard-to-detect long-term errors? Interesting parallel to consider